Previously, we introduced product orientation on manifolds. That might be a bit abstract, and people say a picture speaks 1,000 words, so now let's look at an example, a picture. In this example, we let M be this interval, and let N be this circle, so that M times N is the cylinder. So we'll choose the following orientation on M, and this orientation on N. Now what does that mean? Well, remember that an orientation on a manifold is just a choice of an orientation on each of the tangent space. So when I drew this arrow, this means that for each of the tangent space, for example here, for this tangent space at the point P, I'm gonna choose this orientation, the orientation represented by these spaces. Similarly, here for N, when I drew this arrow, I mean that for any point Q in N, I will choose for the tangent space at Q, I'm gonna choose the orientation represented by these spaces. So now let's see what the corresponding orientation is on this product. So let's look at the tangent space at the point PQ. Then observe that the induced orientation on this tangent space is just gonna be V1, V2. Where V1 here is in this direction and V2 is in this direction, because remember that the orientation map, the value of the orientation map on this ordered basis is just going to be the product of this, and so this is 1 and this is 1. In this drawing, you can think of this as the clockwise orientation. Alright, now let's look at the case when N is actually a disk. Then the tangent space at every point Q on N is going to be two-dimensional. It's going to be a tangent plane. So an orientation should be given by an ordered pair of vector. So let's say we have this orientation V1, V2. As I've drawn it here, this is a counterclockwise orientation. Now let's find the induced orientation on the product M times N here at the point PQ. First, observe that now this is a filled cylinder, so the tangent space here must be a three-dimensional space. And recall that we can think of this tangent space here as a product of the tangent space to M at P, right, with the tangent space to N at Q. So let this W correspond to the orientation on this tangent space TPM, and then on the copy of the tangent space to N at Q, we also have a copy of V2 and V1. Under this identification, we then see that an induced orientation is going to be given by W, V1, V2. Observe that the order of M and N matters here. Alright, up next we're going to talk about boundary orientation, and a specific case is the boundary of a homotopy family. We will use the definition that we just discussed about product orientation for that.